Hi, I'm Elizabeth Sump.
And I'm Fehmida Kapadia.
And we're going to talk to you a little bit here about regenerative medicine. I always want to do like the iCarly random dancing thing after we do this part. But so you guys just got done eating a lot of pizza, so we're going to try and keep this a little bit higher energy so you don't fall asleep on me, because there's nothing I hate more than a carb coma in the middle of my talk. We're going to start with a quiz. Can anybody tell me where in the United States between the two coasts has the greatest concentration of world-class stem cell researchers in the nation? Ohio, specifically Cleveland, Ohio. So you are here, and so are some of the best stem cell researchers in the country. And we're going to talk a little bit about regenerative medicine, and I want to do a couple of things today. We're going to talk about what regenerative medicine is and what it isn't, and Dr. Kapadia is going to talk to you a little bit about what it actually takes to bring a product to market in this field. And the first question to ask is, why focus on regenerative medicine? And let me tell you something. In 2000, Time magazine said that the #1 hottest job in the country was tissue engineer. Now, can anybody tell me how many tissue engineering products have actually made it to market and are successfully commercialized in the 12 years since they made that announcement? Anybody? I'm getting a lot of blank stares. Do you know why? Not a single product has been successfully commercialized in tissue engineering. So why are we doing this? This is my dog. Her name's Bluebird. She's a Scottish deerhound, and she's actually kind of important to this discussion. Bluebird, when she was about 7 years old, started to develop heart failure. And that was kind of early even for a dog of that size. She was only about 55 or 56 years old in people years. And I was really lucky. I had a veterinarian's office close by that actually had a cardiac ICU for dogs. And so she spent 6 days in intensive care in the cardiac unit. It cost me $4,000, which is a lot of money for a dog, but I love my dog. And what's more important is since she came home, she now takes 9 pills a day in 4 different categories for her heart failure. And these are all human, every single one of these are all human therapeutics that we use for treating heart failure in humans. All told, it cost me about $200 a month for her medications. That's a lot of money. But it pales in comparison to what would have cost if Bluebird was a human. If Bluebird was a human, that same hospital stay would have cost $70,000 and the exact same pills. Same package, same brand, same manufacturer, same dosage, would cost $4,000 a year. Here's the kicker. Bluebird still can't run. This is a deerhound. This is a dog that was bred to hunt deer. Her top speed was 45 miles an hour when she was in her prime. She's still a very sick animal, even with all those medications. If we take a look at what it costs us to keep people healthy nationally, we are currently spending 16% of our gross domestic product on health care. How much money do you get in allowance every week? Whatever you ask for. All right. Does anybody here have a job? All right. How much money do you bring home every week?
Probably $40.
You bring home about $40 a week.
Because I only work once a week.
Okay, that's fine. For I'm going to have to take $6.40 of that away from you. Got to pay for your health care, sorry. Okay? Does it make sense for us to pay 16% of our gross domestic product for health care? And we're not, I mean, we're like way up at the top, but most industrialized nations are spending at least 10% of their gross domestic product on health care. And even nations that the politicians call socialized medicine, like Britain, pay 6 or 7 or 8 or 9% of their gross domestic product on health care. This is not sustainable. And the reason it's not sustainable is because we are not spending this money to cure people. We are spending this money to give them multiple pharmaceuticals that have them not getting any better, okay? And so the next story I'm going to tell you, this is my daughter Kirsten, and those of you who've seen this talk before know that my daughter died 3 years ago. She was 9 years old. She died very suddenly of an arrhythmia that was not detectable, and the type of arrhythmia she died of is almost always fatal in girls, okay? That is not why she's up here. She's up here because when she was 3 years old, I asked her, "Baby, what do you want to be when you grow up?" And do you know what she said to me? "I want to be a heart doctor, Mama." Now that kind of surprised me because when I asked her little buddy next door what he wanted to be, he told me he wanted to be a pig. But I said, "You know, baby, why do you want to be a heart doctor?" And she said, "Well, you know, Grandpa's heart doesn't work, and I want to fix it." Because even at the age of 3, a 3-year-old kid could see that a man in his 60s on a pacemaker was not having a very good quality of life. And she came back to me when she was 7. She goes, "Mama, why don't doctors make people better?" And I said, "What are you talking about?" She goes, "Look," she says, "Grandpa takes 8 pills a day." She says, "And he still doesn't feel good. And if he stops taking his pills, he's still really sick. I thought doctors were supposed to make people better." And that's why we invest in regenerative medicine. Because regenerative medicine is about actually correcting the deficits that we have from disease or from genetic illness or from trauma. Okay? This is about actually fixing what's wrong. Pharmaceutical companies, incidentally, really hate this because we're hoping to put them all out of business. So I'm going to ask you guys a question. All right, ready? Raise your hand if the very first time I say stem cell, the first thing you think of is embryonic stem cell and you have kind of a little bit of an emotional thing. Be honest, raise your hand. Raise your hand. Oh, look at that. This is a really small number. This is great. Only about 5% of you. I love high school students, okay? When I give this talk to business people, about 60% of them raise their hands, okay? Let's be clear about what stem cells are and are not. A stem cell is any cell that has the capacity to replace itself and also to do something we call differentiate, which means to go down a particular path and specialize and get really good at doing 1 or 2 things and decide not to do all the other things. So we have stem cells that are capable of making bone and muscle and blood and livers and nerves and things like that. You, high school students here, make about 60,000 stem cells a day. Older people like me, we make about 30,000 stem cells a day. There is a very specific name for the condition for people who do not make stem cells. Do you know what it's called? We call it death, okay? And it means because when you stop replacing things like your red blood cells and your hair and your skin and your liver and your bone marrow, that's when we die. And we get less good at it as we get older. That's why we eventually die out. But you are alive because you make stem cells every day. Where do stem cells come from? A lot of the ones that we work with are taken out of bone marrow, so what we call connective tissue progenitors, what we call, these are naturally occurring stem cells that can make bone and cartilage and ligaments and tendons and stuff like that. MSCs and MAPCs are a special kind of cultured cell that we take out of bone marrow and we make specialize a little bit in the laboratory before we use them. But we have neural stem cells, we have skeletal myoblasts. Umbilical cord blood cells are a very important source of stem cells. When people give birth, we get the umbilical cord and the placenta, and those are full of stem cells that are not derived from embryos, but have almost all the same characteristics as an embryonic stem cell. One of my favorites, the adipose stem cell. Adipose is another word for fat. Part of the reason we gain weight so easily is because we have a ton of adipose stem cells. In fact, in bone marrow, only about 1 in 20,000 cells is able to make new bone. In your fat, 1 out of every 10 cells in your fat is capable of making more fat. Okay? But here's what's cool about it. If you feed adipose stem cells certain types of diets, like a diet that's low in glucose and high in other types of nutrients, you can actually get those stem cells to make muscle and to make bone and things like that. If I take a bone stem cell and I feed it too much glucose, do you know what it turns into? Fat. So we're learning how to better utilize the stem cells we make every day in our body. A type of engineered cell that has become more popular is what we call the induced pluripotent stem cell. And this is where we take a differentiated cell, a cell that's already specialized like a skin cell, and we can use a virus that can infect it with 4 specific proteins, and that causes those differentiated stem cells to do something we call dedifferentiation, and they turn into genetically identical cells that look an awful lot like embryonic stem cells. We call them induced pluripotent cells. And those are capable of redifferentiating into a lot of other different types of cells. Now, we're going to take a minute and talk about why pluripotency sometimes isn't good here in a second. But one of the things that we found is that these are really hard to control at times. No differently than embryonic stem cells can be really hard to control. So what's emerged in the last year or two is that we've actually learned we don't need to get them all the way to pluripotency. We can actually take stem cells that are already differentiated, and by mixing around the cocktail of proteins that show up at different times, we can actually get them partway down the path and then take them up a different path. So we can take skin cells, turn them into nerve cells. This is very, very powerful. And what it means is that we can do a better job of using the cells that each of us produces ourselves to fill gaps and to replace tissues as we need them. Most of the stem cell research that's done here in Ohio is focused on non-embryonic stem cells, and I want to be very, very clear about something. Has nothing to do with politics, has nothing to do with religion, has nothing to do with what we think is ethical and what is not ethical. It has everything to do with the fact that you live in Ohio where we make stuff. Okay? We're focused here. It's one of the things I love about living in Ohio. You know, we can let people deal with kind of the whizzy out there going to be 20 years before it's any good kind of stuff on the coast if we want to. But when it gets here, by golly, we want to be able to get it into a human being and doing some good work in a couple of years. And we know a lot about how adult-derived stem cells act when we work with them. So we're focusing on those right now. We may move more into embryonic and induced pluripotent cells if we need to. We may or may not need to as time goes on. I also want to be really clear that when we talk about regenerative medicine, I've talked about cell-based therapies, but it's not just about cell-based therapies, okay? So other things that we do here that support regenerative medicine, we make what are called bioscaffolds, which basically give those cells a great place to live. And when I talk about wanting to take advantage of all those great stem cells you make every single day, you have to give them a place to live, and you have to get them to show up where you want them to, right? And so we spend a lot of energy producing things like growth factors, which are proteins that make cells grow in a particular direction, or what we call homing factors, which are like sending up a great big flag that says, hey, cells, show up over here where we need you to be. And so to the best extent possible, we're going to focus on using the stem cells you make every day. But we also are focused an awful lot on finding better ways to when we do take cells out and do something with them in the laboratory, doing that in the most efficient, effective way possible. State of Ohio's invested about $40 million in this so far through the Third Frontier campaign. We've brought about $300 million in other funding into the area to work on this. One of the places that funding has come from has been the Department of Defense and the Armed Forces Institute of Regenerative Medicine, which I've been very privileged to be part of for the last 5 years. And that's a consortium that goes across the nation. Here in Ohio, we've actually advanced 4 new technologies all the way into clinical trials out of the AFFIRM. One of them has been the use of what we call composite tissue allografts. Those are face and hand transplants to better treat injuries that we simply cannot treat. They're catastrophic injuries. We can't treat them any other way. We've found better ways to use bone marrow cells from the patient's own bone marrow to regrow bones that simply won't heal. We have engineered skin substitutes that we can use to treat giant burn injuries. I got a guy down in Cincinnati, you guys. He can take a piece of intact skin the size of the palm of your hand, and in 4 weeks, grow enough of your skin to cover 90% of your body with your own skin. It doesn't scar. These patients don't have to have multiple skin grafts. They can actually get their own skin back. And it's not uncommon anymore for us to save patients who have 90% total body surface area burns. We've got new advanced arteriografts. But we'd like to take a second and drill down into a particular type of new technology that's being developed at the Cleveland Clinic. And Dr. Kapadia is going to come up here. She's going to talk to you about what it takes to get one of these products into the marketplace. And if we have time, I'd love to drill down and talk about some of the other technologies we're working on here. Okay?
Thank you, Beth, for an excellent introduction.
So Beth talked about adult stem cells, right? When I think of adult stem cells, I think of two main sources of adult stem cells. One is autologous stem cells, which means that if I got sick and I needed treatment, the doctor would take my bone marrow, purify it, clean it up, grow out my stem cells, and then put it back in me to treat me. And the other source of adult stem cells is allogeneic stem cells, which means if I got sick and I needed treatment and for some reason the doctor couldn't use my bone marrow, and Beth here loves me very much, she wants to make sure I get all right, so she says, all right, take my bone marrow. We get Beth's bone marrow, it gets cleaned up, the cells are expanded, grown out, and put into me for my treatment. So this cartoon shows very quickly what happens once you isolate the cells or isolate the bone marrow from a donor or a patient. The first petri dish here, as you can see, as soon as you take this cells out and you plate it, it's a mush of cells, right? You have your red blood cells, you have your white blood cells, you have platelets, you have all kinds of things in it along with your stem cells. Once you plate it and you let it grow for a certain period of time, a few days, then you start seeing these colonies. What these colonies are these are your stem cell colonies. And I'll show you this. This is a representative of a plate from our lab. These are osteogenic stem cell colonies, which means that they can form bone. The reason these colonies are red is because they're bone forming, which means they express calcium, and they've been stained with alkaline phosphatase, which stains them red. So in this plate itself, although they all form bone, you can see a heterogeneity in the population, right? You have these big colonies, and then you have these really tiny ones, and then you have some of these which stain dark in the middle and then really light on the edges. And so what's happening right now is this is a pool of the colonies that I showed you. What we currently do is we pool all these colonies, and that's what we use for treatment. Now, what if we don't need to pool all the colonies? What if what we need is this green colony, which we have found is the most efficient for treatment, right? If these colonies keep growing, you have these blue guys, you have these red guys, they are the faster growing cells. So they're going to slowly start taking over the population, and now you're going to have a mixture with the green colonies constituting a very small population of your stem cells. So what our device can do is, very early on in the process, we can go in, we can pick out this green colony, we can cherry pick this colony out, and then we can plate it. And now you can have a plate of just green colonies, a relatively pure population that we know would have documented efficacy. So what we have developed is, what we call our product right now is Smart Selector. Smart Selector is a combination of Colonize, which is this really cool software that we've developed in the lab, which can detect these colonies based on various criteria that we can specify. And we are working with a local company called Parker Hannifin. Parker Hannifin is a Cleveland-based company. It's headquartered in Cleveland. Parker Hannifin started in Cleveland, and today it's a global multi-billion-dollar industry. So we are partnering with Parker Hannifin, which is a manufacturing company. They have expertise in robotics, fluid dynamics, things like that. So they're working with us to build the robotic arms required to go in and pick up the colonies with their smart syringe technology. So that's a little bit about the product that we are trying to develop, and I'll give you a little bit of an idea of what it takes and how long it takes to develop a product. So the first ideation for Colonize was somewhere around 2003, when we felt the need for something like this in the lab. In our lab, we work with connective tissue progenitor cells, and we used to do a lot of things manually, And the need was, geez, I wish we could automate this process. And that's how the idea for Colonize was born. And so he started developing something, a software that would help us automate the process of identifying these colonies. And so started the process of technology validation over a span of 3 to 4 years. We worked on validating the technology, making Colonize work, and then in 2006, we filed our first patent. The patent was issued in 2010, so it takes about 4 to 5 years after you file your patent to actually get approval. And at that point of time, we started developing a prototype. We started working on developing. We knew we could do this in the lab. We could do this on the cells that we are using in the lab. We thought, well, I'm sure this can have applications for other people too. There is a lot of manual identification going on, and we could help others do the same. In 2012, at this point of time, where we are is we are very actively engaged in doing feasibility assessments. We have proven that the science and the technology is very solid. We are very confident about that. And so now what we're thinking about is, what does it take for us to take this product to market? How do we sell this product? How do we develop this product? What we have right now is a prototype. How do we make it into a commercially viable product that people would want to buy from us? So that's the technology assessment part of it. And then the market assessment part of it, which I'll go into greater detail in my next slide, deals with all the market assessment pieces of what it takes to take a product to market. We anticipate that the way things are moving right now, by next year, we should be able to enter the market with our first commercial product. And by 2014, we start to have actual regular customers for this product. So, as I said, let's go a little bit deeper into what it takes to do market assessment. You guys are familiar with what it takes to do the science, well, a little bit of it. So if I want to start a business with a scientific product, what are the things that I need to take into consideration? First, I need to think about, where am I going to sell this product? Who is going to buy my product, right? So what is my market segment? My market segment in this case would be researchers that are working with stem cells, companies that are working with stem cells, and core facilities that are working with stem cells. Anybody who is developing things that allows, that they need help with to automate it, they are our customers. Next thing we want to know is, what is our competition, right? So who else is out in the market? What are they selling? How good is their product? How does our product compare with their product? How can we make our product better? Is what is currently available in the market doing what needs to be done? That is a competitor assessment portion. Regulatory. This is very, very important, because to get any healthcare product into the market, to use something for patients, you need the FDA's approval. You need the FDA's nod. We have to go through various regulatory routes to get an FDA approval. And so that's the other piece of assessment. Funding. Where am I going to get the money? It takes a lot of money, a few $1 million, to develop a product like this and bring it to market. So exploring what are our sources of funding, where can we get the money from? And lastly, customers. Who is going to buy? How are we going to get people to buy our product? Because although there is a need in the market, everybody has a way of doing it, right? So maybe they don't realize that they need a product like this, or maybe they don't want to change the process that they're currently using. And how do we convince people that this is something that would make their lives better, and this is something that is good for them? So what we plan to do, and this is generally a fairly regular route if you're thinking about scientific products, when you're developing something, you try and establish collaborations with other researchers and people who are working in the area, so that they get interested in your product, they are willing to try your product, give it a shot, and if they like it, then we convince them to buy it from us. So that becomes our first adopters, and once you have your first adopters, you can you start building up credibility and start increasing your customer base. So that's the overall market assessment piece that we do. As I said, our expected launch date in the market is 2014, and very much looking forward to it.
So a couple of thoughts to leave you with. And the reason that we wanted to take some time to have Dr. Kapadia go over the actual steps of product development is that a lot of people think about development of new healthcare and technology products as the technology being the barrier. The technology is almost never the barrier. If you are going to be effective entrepreneurs, if you're actually going to be able to make a difference in the lives of your customers, in the lives of, in healthcare, in technology, you have to think about the whole process. You have to think about whether or not somebody can make money off of it, because like it or not, money drives things here. You have to think about what are you going to have to do in order to manufacture it, what problems is it going to solve, and I'm challenging each of you, same as you had with your morning speakers, to look at the whole package. Many of you are going to be taking on year-long projects to develop a new product idea and a business plan around that. You have to think about all of it, not just the science.